Hello everyone, my name is Avirhotra Gali, and today on July 20th, 2025, I'm here to present to you about a new, exciting, and interesting technology with much potential to revolutionize neuroscience and global health called a brain-computer interface, or a BCI. Before we dive into BCIs, I want to introduce myself to you guys. I live in Aldie, Virginia, and I am a rising sophomore at Johns Hopkins High School. I'm a student researcher and I'm part of a neuroscience lab, and I'm part of the GYEL program. Additionally, I am a sprinter for my school's track team and specialize in the 100 meter, 200 meter dashes, and I play the violin for my school's orchestra. Now let's dive into brain-computer interfaces. What is a brain-computer interface? A brain-computer interface is a system which connects the brain to an external device or an application. What this means is a BCI can detect, by recording the brain activity in the brain, it can detect the brain's intent, what the brain wants to do, and it converts that intent into commands, which are sent to external applications, which carry out that command. Said applications could include robotic arms, neuroprosthetics, a computer, a wheelchair, or any external devices. And the way this works is brain activity is recorded through a device first, and then the signal is then processed, classified, epoched, analyzed, and then the command is sent to the application, which once it carries out the command sends feedback back to the brain, telling the brain that the operation was carried out. So just to show how BCI has grown over time, lots of more papers are being published and a lot more research is being done on BCIs as time has passed, and a lot more knowledge is being spread about BCIs. And now people are looking to incorporate AI into BCIs to make it more smarter and to make it better able to identify the commands the brain signals are telling the device to do. And the BCI market has also been growing. People are investing in BCIs due to its potential, and many startups are being created too. Now let's dive into what brain activity means. I said that BCIs record brain activity, but what is brain activity? So the technologies which detect and record brain activity are known as BCI modalities. And these BCI modalities detect either one of two brain activities: electrophysiological activity or hemodynamic changes. Electrophysiological activity refers to electrical activity generated by neurons when they communicate. Basically, what this means is neurons are part of neural networks in the brain, and each neural network has its own function to maintain to regulate body processes, to execute functions, or to understand external stimuli. And whenever these neural networks are in use, or whenever they are functioning to carry out a function, the electrochemical signals are passed between the neurons in the neural network, and this electrical activity is detected by the BCI modality, trying to detect electrophysiological activity. Next, we have hemodynamic changes, and this refers to the changes in blood and oxygen levels in response to brain activity. Simply put, whenever regions of the brain are being used, they require more oxygen. And in order to fulfill this need, the body sends more oxygen rich blood to these regions of the brain. And this change in oxygenation of the blood is detected by certain BCI modalities. Now let's dive into the types of BCI modalities. There's non-invasive and invasive. Non-invasive BCIs are placed on the external surface of the scalp, on top of the scalp. They are much easier to use and more accessible. There's no risk of brain tissue injury, and they are much cheaper than invasive BCIs. But they're also less accurate because they're distanced from the brain. They're susceptible to external noise or things like hair, which can get in the way of the sensors trying to record the brain activity. And they're too superficial. They're not targeted on a specific brain region. Now we have invasive BCIs, which are implanted directly onto the brain tissue, onto the brain surface, and they provide greater accuracy. They can target specific neuron populations due to their proximity to the brain, and they have long-term stability. They can be left in the brain for a longer amount of time. But their cons include risks from brain surgery, and they are very costly. So here are the electrophysiological modalities. We have the EEG, or the electroencephalography, ECOG, intracortical devices. An example of the intracortical devices is the LFP or spikes, and the magnetoencephalography. This is an example of an EEG. An EEG is this cap placed on the scalp, and these are the different sensors which detect the voltages of the neuronal activity in the brain. And these voltages are shown through oscillations, as can be seen on the right of the screen. And these oscillations show whenever the participant thinks of something, how the activity in the brain spikes or doesn't spike. And this can then be translated to the application to classify and understand the intent and how the intent is shown in the oscillations. Next, the ECOG does the same thing, except it's placed on the surface of the brain underneath the scalp, beneath the scalp. And then the intracortical devices, LFP and spikes, do the same thing too, except the spikes are inserted into the brain tissue and record the brain activity of individual neurons, which is then sent. So this is the spikes. It's activity of the individual neurons, and the LFP puts it all together and shows the general neuron populations of the brain in that region and how the electrical activity has been changing. And now let's talk about the hemodynamic modalities. We have fMRI and FNIRS. In an fMRI, the patient is placed inside an MRI machine and are told to do a certain action, such as speaking, tapping their fingers, or listening to something. So that if they tap their fingers, we can see that this region of the brain required was being used. Hence, it required more oxygen-rich blood. Hence, we can see that there's an increase in the oxygenation levels of the blood in this region of the brain, showing how this region of the brain was used. Next, we have FNIRS. And FNIRS stands for Functional Near Infrared Spectroscopy. And what this means is that whenever a patient is set to carry out an action, infrared light is shown onto their brain surface. And what this does is through the infrared light, it can detect the blood flow to the brain, and can detect how the oxygenation levels of the blood are changing. So, and through this, we can see where the blood is flowing in the brain when a patient does a certain activity, and how the blood flow and how the blood oxygenation levels in their brain are changing. Now let's dive into the different startups. The different startups include Neuralink, Synchron, Precision Neuroscience, BlackRock Neurotech, and Neurable. These are some of the notable startups. Neuralink is well known due to Elon Musk owning it. And Synchron created something called the Stentrode, which is an implant which can be sent through the jugular vein into the brain, and it's great for recording electrical activity. Additionally, BlackRock Neurotech invented the Yuta Array implant, which has helped over 30 people control an external device with their using their brain, and has helped 30 people restore their movement and speech. Now let's go over BCI's applications. In general, BCI is useful for neuroprosthetics and neurorobotics, controlling external devices, external arms, external body parts using the brain, greatly helping people with degeneration of muscles over time. And then additionally, there's stroke rehab, which helps people who have a stroke in which certain brain regions forget how to function. It helps reteach those brain regions how to function, how to move, and how to signal the body to carry out a certain function. And then it's great for monitoring and early detection of epilepsy, Parkinson's, Alzheimer's, and it's great for education and cognitive enhancement, as it can teach the brain the best way to learn, the best way to critically think, and the best way to memorize stuff. And in relationship to global health, it can greatly improve quality of life. The people with ALS, the people who can't speak, people who can't move, will be able to communicate with the world and people around them through these brain-computer interfaces. It also drives brain research, as it helps people understand lots about the brain, how the brain functions, what the brain thinks, whenever it wants to body to carry out certain functions, and can by extension help find cures for certain of the neurodegenerative diseases. It also helps in disorder support for autism and ADHD, helping people with those disorders figure out the best way to learn, the best way to live life. And it helps in disability inclusion, helping people with disabilities interact with the people and world around them. Thank you for listening to my presentation, and here are my references.